This video will cover join operations in relational data. By the end of this video, you should understand the common types of joins used on relational data and how each of the different join types differ from each other. In the last video, we covered relational data. Remember that data you want often involves combining information from many separate tables. The example that I provided there had a customers table and an orders table, where orders for each customer were linked to the customers table using a customer identification number. But how is it that we actually combine the information from these tables? Relational algebra is a formal system for combining data contained in multiple tables. We define relationships between tables. A relationship is a variable or set of variables where identical values of those variables define observations that should be matched to each other. We actually combine the tables using join operations. These are similar to mathematical operations, and they define how data should be combined from each table. Relational algebra is a core concept in data science workflows. It's reproducible. Every join operator is well defined and will produce consistent output given a consistent set of inputs. Likewise, it's transparent. Each join operator has a well understood meaning, which describes the intent of the person writing the code as to how they would like to combine information from different data sources. How is it that joins work? As I said, they work like many other mathematical operators. A join takes two sets of data as its arguments, and it returns a single set of data as the result. Unlike some of the mathematical operators you're familiar with, join operators may not be commutative, so the order matters. Multiplication is commutative. X times y is always equal to y times x, but division is not commutative. X divided by y is not the same as y divided by x. The order matters. It's very much the same with join operators. When order does matter, we're going to identify one table as left and the other as right. Joining data between tables also requires defining relationships. Remember, this is one or more variables that are common to both tables, where values of those variables being identical defines observations that should be matched to each other. Importantly, a natural join is going to assume that all variables with identical names from both tables form the relationship. So when performing a natural join, you'll look at the list of variables in each table. Every variable name that occurs in both tables is assumed to be part of the relationship between those tables. The resulting table is a combination of information in the two tables. It's going to have one observation for each possible combination of matching relationship values. This means that the resulting table may have more observations than either of the source tables if there are multiple matches between individual values of the relationship variables. So let's take a look at how this works. I've recreated the tables that we saw in a previous video. I'll just make you aware that I've added a new customer ID 14, Lando Calrissian. But notice that Lando Calrissian has no orders in the orders table. Remember that we have a primary key in the customers table, cust.id, which uniquely identifies each customer. That shows up as a foreign key in the orders table. This tells you how each order maps back to an individual customer. To start with, we'll think about combining these tables with a natural join. The only common variable name between the two tables is this cust.id, and we'll assume that variable forms the relationship between the two tables. So how does a join between these two tables work? Looking at the customers table, cust ID 12 corresponds to Luke Skywalker. In the orders table, there is one order with cust ID 12 for one laser sword. The joined table has a record, customer ID 12, Luke Skywalker, for one laser sword. Moving down in the customers table, customer ID 18, Leia Organa, has one corresponding order record in the orders table for a bounty hunter disguise, quantity of 3. The resulting joined table includes that information. Moving further down the customers table, customer ID 7, Han Solo, has two corresponding orders in the orders table, one for a spaceship and one for 15 units of Wookiee Chow. The resulting joint table now has two records, one for each order, preserving that customer information, cust ID 7, with the customer's name as Han Solo. Finally, moving to the last row of the customers table, customer ID 14, Lando Calrissian, has no corresponding orders. This means the last row of the joined table has customer ID 14, Lando Calrissian. There are no corresponding product orders, so you have NA for both the product name and the product quantity. So in this example, Lando Calrissian doesn't have any orders. Do you want that Lando customer to show up in the orders table? I'll tell you that you definitely maybe want that observation there. Which observations you want to include in your output table depends on what you would like to do with the data. Suppose you want to compute total sales per customer. Do you want Lando in your data in that case? Lando is a customer and shows up in the customers table. In this case, you'd probably like to include Lando and just know that Lando has spent $0 on orders so far. In contrast, if you wanted to compute average dollars per order by customer, you may not want to include Lando in your data because he hasn't placed any orders yet. Because you may or may not want to include non-matching observations, relational algebra defines several different join types that allow you to keep or exclude observations when they don't have matches in the corresponding table. Each of these join types is going to keep different information depending on how the key variables match between tables. You can keep all, none, or some of the observations with key variables that don't match between tables. So let's go through the common join types and how they'll create the resulting output table in this example. First, there is the full join, which is sometimes called an outer join. This is going to keep all observations from both tables, regardless of whether or not they have a match. Observations for which there is no match will have missing information. In R, this would be an NA value. So if I were to perform a full join on these two tables, I would have this resulting table here, where the Lando Calrissian customer is included, and I have NA values for the product and the quantity because there's no corresponding order. In contrast, an inner join only keeps observations with matches from each table. This means that in the resulting table, the customer ID occurs in both the orders table and the products table. So each variable in the join table should have a value unless there is missing information in one of your input tables. Sometimes you'd like to keep matches from one table but not another. A left join is going to keep all observations in the left table and only observations from the right table where the key variables match between tables. Observations from the left table that don't have a match in the right table will still show up in your output, but you'll have missing values, or NAs and R, for the missing information. In the example that we have here, a left join would keep the Lando Calrissian customer record, but again, we would have NAs for the product and quantity because there's no corresponding order. In contrast, there's a right join. This keeps all observations in the right table and only observations from the left table where the key variables match. As with the left join, observations from the right table that don't have a match will have missing information. So in this example, because Lando Calrissian does not show up in the orders table, there's no Lando Calrissian record in the output. A very different type of join is an anti-join. Sometimes you want to know about observations that don't match between tables. An anti-join is going to give you a table of observations that don't have matches in the corresponding table. The way this works is an anti-join keeps one copy of each observation in the left table that does not have a corresponding match in the relationship variables in the right table. The resulting table has the same columns as the original left table. Obviously, you don't want to include information from the right table because there are no corresponding matches. In this case, if we were to perform an anti-join, the resulting table would just have cust ID of 14 for customer Lando Calrissian, because that is a record in the customers table that does not have a match in the corresponding orders table.